Welcome back to the Pack Hero Festival. So we have another performance rockstar that was part of the Q&A of Tuan's session. It's Stefano Doni. So he's going to talk about Java performance in 2021. So Stefano is working for Akamas. Has built an awesome platform based on AI that do automated tuning, automated optimization based on objectives. So it's a pretty awesome product. Otherwise, Stefano is highly passionate about performance. So he won the best paper award at the CMG International Conference in 2015. So it's going to be a very interesting presentation. I can guarantee that.
Hi, everybody. Thanks a lot, Terry, for the great introduction. Welcome to my session on Java performance in 2021, how AI optimization will debunk some four long-standing Java tuning myths. So let's get started. So a quick intro about myself. I'm Stefano Doni, so I have about 16 years of experience doing capacity planning and performance optimization work. So over the years, I've presented some of the results of my work in international conferences like CMG. And more recently, about 5 years ago, I actually started working on a new idea of using AI and machine learning to automatically optimize the performance of applications. Later on, that idea became a product and a company called Akamas, which I co-founded in 2019. Oops. So let's get started. So first of all, I want to introduce to the topic of Java performance tuning and why it is important for performance engineers. Then we will see how do people do performance tuning today and where does AI fit into the performance tuning process. So Java performance optimization is a pretty broad topic. So the main focus of today's talk is on JVM performance tuning, which means optimizing application performance, not touching the application code itself, but tuning the JVM virtual machine configuration settings. So Java is a very popular platform and lots of material has been published over the years on how to tune the parameters of a JVM to extract more performance or reduce the infrastructure cost of running Java applications. So it's still a hot topic today. You can see here just a sample of some of the great articles that were recently published on this topic. As we are going to see in this presentation, the benefits of JVM tuning can be very significant on both application performance and also infrastructure cost. But besides that, JVM tuning is also important to ensure service reliability. As you can see in this example that I took basically a screenshot from a project that we did for a customer, JVM tuning significantly imparts the ability of a Java service to sustain peak traffic levels without service disruptions. So in this chart, you can see the throughput of a Java application under increasing level of load. The orange line is the throughput of the service with the default JVM options. You can see that the service basically started to slow down under peak load and then crashed. Conversely, the exact same service with tuned JVM settings was able to sustain peak traffic levels without service disruptions. So why JVM tuning is such a hot topic today? So I'd like to quote this great book here by Scott Oakes from Oracle itself. It's a fantastic resource that I definitely recommend if you want to learn more about the JVM internals and how to better tune JVMs. As Scott mentions, the JVM tuning is an essential activity for many companies. If you are not into JVM tuning, it may be surprising to know that JVM is an extraordinary piece of software, and it's also highly configurable. It literally has hundreds of options that we as performance engineers can tune to achieve optimal application performance. If you are wondering about how many options a modern JVM actually has, here you can see the number of settings actually across the different JDK releases. Java 11 is the current most widely used JDK, and it has more than 800 total configuration options, so a pretty staggering number, of which I would say more than 100 can have a performance impact. So there's definitely quite an exciting optimization potential that is available for us performance engineers to exploit. So we have seen that JVM tuning is an essential process, but the JVM itself is a very complex machine. So how do performance engineers do JVM tuning today? So I speak with a lot of teams doing performance optimization. What I see is that JVM tuning, like actually more generically, the performance tuning is typically an iterative and trial and error process, where basically we test the performance of our application, we analyze the application and the JVM key performance metrics like the garbage collection time. We decide to change some VM options like the garbage collection, the heap size, etc. We then apply the new changes and we run a new test. And finally, what we do is we compare the result that we achieved against the baseline performance. So to guide us in this tuning process, we basically rely on vendor best practices like the Java Performance book that we have just seen to provide us some performance models that we need to keep in mind to reason about the JVM performance. For example, to assess if there is a need to tune the JVM garbage collector. The key point of this talk is to look at a couple of those Java tuning best practices or belief, actually, and to see if they are actually true. To do that, let me first introduce the role of AI into the tuning process and how did we come to question the beliefs that we have always used. So where does AI fit into the tuning process? AI is changing entire industries, and there are many discussions about how AI can help the performance engineer become more productive and deliver more value. One way where AI can really bring a lot of value is making the performance tuning process more automated, faster, and making it more scientific. There are key, actually, major benefits of incorporating AI into the performance engineering process. First, AI can be used to navigate the hugely complex optimization space of JVM options. There are literally millions of combinations, and it's easy for the human brain to get lost, even for the performance expert, even for the vendors themselves. Second, the optimization process can become really goal-driven, and this is key. We are going to see why in this talk, meaning that the performance engineer will state the objective of the optimization in terms of business or application metrics that we want to minimize, like the transaction latency, or maximize, like the transaction throughput in business terms. And we let the smart system take care of the actual tuning. Third, the process becomes more scientific and automated, where the automation includes not just the launch of the performance test, but basically all the steps, the analysis of the test results, identification of the best settings that we're talking about, and the configuration of the new settings to the target system in a more automated fashion. So we are now ready to start debunking our Java performance myth. So at Akamas, we used AI to optimize hundreds of Java applications, and we got some very unique evidence in this process, so I'm happy to share them with you today. So let's get started and see what we as performance engineers can learn by looking at the results that AI was able to achieve. So let's start with the first myth. So if you are into JVM tuning, you know that the main target of tuning is actually the garbage collector. The GC is the process that JVM uses for memory management. So a huge focus is put on making the GC run faster so that it won't impact the performance of our applications. But are we really sure that this is the right thing to do? Let's look into more detail. So to let you better understand this myth, let me quickly define some key performance metrics of the garbage collector. So in a nutshell, the main task of the garbage collection is basically to free memory. But to do that, it has to stop the application threads. The amount of time it stops the application threads is called the GC pause, and the percentage of time spent doing garbage collection is called GC overhead or GC time. Throughput is the percentage of time that application threads work. So if I have 20% of GC time, my throughput will be 80%. Last property is footprint, which is how much memory or CPU the JVM actually requires to run. So having said that, here is the golden rule of garbage collection performance. You need to lower garbage collection time. So if you think about it, it makes totally sense. If we decrease the garbage collection time, we will get higher throughput, meaning that the application threads will run for more time without being stopped. I took this chart from the official Oracle docs as it shows the negative impact of garbage collection time on the application throughput and also on the scalability as you add more processor. So it makes totally sense to minimize garbage collection time. This performance rule is so ingrained in our industry practices that it is one of the main best practices that we use in our JVM tuning activities, and it is even implemented by market-leading APN tools to identify memory pressure within the JVM and to suggest the need of JVM tuning. But I'm going to show you that GC overhead isn't everything. And if we blindly follow this rule, we can actually end up making our application run slower instead of faster. So here you can see the result of an AI-driven optimization where we had a Spark application running on OpenJDK 11, and the goal for AI was to minimize the execution time of the Spark job. So in the chart, every dot you can see is basically an execution of the application with different JVM options. For each execution, we measure the execution time and the GC overhead. The yellow dot that you can see is the baseline configuration, which is the JVM with default settings. You can see a couple of very interesting and counterintuitive results here. So first of all, the best configuration was about 30% faster than the baseline. So a pretty significant result AI achieved with optimal JVM options without touching the code again. But look at what happens at GC overhead. So the best configuration actually had a higher garbage collection overhead, almost actually 2x with respect to the baseline. So it's very interesting to observe the shape of this curve. It's very different from what the theory and the performance model that we have just seen. We might have expected a more kind of linear relationship, meaning that the higher garbage collection overhead, the higher the execution time. But instead, we got this kind of curve where the minimum execution time is actually achieved with about 30% GC overhead. Please note that this level of overhead is pretty significant. Just to give you some numbers, some APN tools warn about a high garbage collection overhead with about 15%, so about half of what we got here. So I think the reaction of performance engineers to this kind of situation would be to add more memory to relieve the JVM pressure. But again, this is not what AI did. AI did not follow the best practice, but it followed the goal that we have asked, which was to minimize the execution time. And it found a very counterintuitive configuration that no performance engineer would actually ever suggested, but it actually had a pretty interesting result, being letting the application run 30% faster. So the result in itself is super interesting, I think, from a performance engineering perspective. But the key question is, how is that even possible? There can be several ways in which garbage collection interacts with application performance and the underlying hardware that can explain what is happening here. So let's dig deeper into the inner workings of the JVM to understand what is happening. So what did we do? So we used a tool actually to trace the JVM threads and see how they are scheduled by the Linux kernel into the actual processor and see if we have any kind of bottlenecks on the CPU here. So this graph shows a visualization of the different threads of the Spark JVM and how they are scheduled on the CPUs. There are a couple of tools that you can use to generate this kind of chart. Here I use a tool that is made by Google, which is called Perfetto. It's an open source tool that it's actually being used by Android developers to diagnose performance issues on mobile applications, but the same technique can be used for standard Linux app and for the Java-based application. So what the scheduler traces are telling us, what you see here on the rows are the various threads within the JVM. So at the top, we can see the Spark application threads that are called executor tasks. Those are the actual application threads. At the bottom, we can see the garbage collection threads. So those are the JVM threads that perform actual garbage collection work. So for each thread, you can see that the running bar, which means that the thread is running on the CPU. So the first thing to notice is the garbage collection pause in action. You can see that the application threads are stopped and then they resume after the garbage collection pause has completed. But if you look closely, you will notice that there are some garbage collection threads that are executed concurrently with the application threads. As you can see, they are called G1 conc threads, and this is a design feature of the G1 GC, which is the default garbage collector for OpenJDK 11, which actually is using background threads to perform part of the garbage collection process in order to reduce the stop the work pause, which is one of the goals. But the important thing to notice here is the color of the bars, where a thread is marked as dark green if it's running on the CPU, and in light green if it's actually waiting to access the CPU. So then here comes the explanation for the application slowdown. So the G1, GC concurrent threads are actually competing with the application threads to access the CPU. As you can see, there are some application threads that actually becomes runnable when the G1 concurrent threads actually starts running. So this means that the G1 threads are actually stealing the CPU access from the actual application threads. So why are those phenomena actually not reflected in our GC overhead matrix? The key point is that the GC time or GC overhead metric does not consider this concurrent garbage collection work. It is just a metric that says that actually measure the amount of stop the word pause. So it's totally not considering this kind of interference that we may have between concurrent garbage collection works and our application threads. So it's interesting because in this case, you see, if we tune the garbage collection to decrease actually the stop the word pause, we might actually cause more harm than good, because we might actually be asking the garbage collection to do more work, more concurrent work, which can actually slow down the application threads for much more time. So data tells me that this myth is actually busted. So the key takeaway here is that garbage collection time is an important metric, but we need to remember that JVM performance is not application performance. So actually, the simple garbage collection overhead performance model that the books, in a way, is teaching us might not work, as the JVM is a complex machine and sometimes work in a kind of unpredictable way, which may lead to slower application performance or higher resource usage. So that was it about the first myth. So let's now move on to the second myth, and this one is another classic. So this principle states that if we consider throughput, response time, and footprint, you can really have just two of the three. So if you want to have high throughput and low latency, for example, you will need to have a large infrastructure footprint, because the garbage collection will need more memory to make room for application allocation without stopping the thread too much. On the other side, if you want a low footprint and high throughput, you will need to accept that you will have higher latency, because the GC will probably need to stop the application very often to keep up with the application thread running as much as possible. So it looks like this is a kind of law of physics that we cannot really escape. But are we really sure? Let's see what we have found out. So this is another very surprising result that we got by tuning an enterprise Java application, this time using AI, where the goal was to minimize the footprint in terms of JVM heap size while maintaining the same level of performance. Let's look at what AI achieved. So the throughput of the application increased by 23%, and the response time actually decreased by pretty much the same amount. So a pretty good result here. But what is more interesting is that AI managed to make the application run faster, while at the same time it reduced the heap size by more than 80%. So how counterintuitive is that result? So reconfiguring the JVM actually improved all the three key performance metrics and cost metrics of the application. So how can we explain a result like this one? So unfortunately, we couldn't get more low-level data on this case, because it was a customer environment, and due to time constraint, we couldn't get more access to more lower-level metrics. But we managed to reproduce this kind of behavior in our labs. So unfortunately, I don't have time today to share all the details, but feel free to get in touch with me via LinkedIn, and I will be happy to share the rest of our findings with you. So again, back to our myth. If we look at the broader application performance picture, data shows that this myth is actually busted. I think that this principle is actually true if we look only at the specific garbage collection implementation. You can really get low latency, high throughput, and low footprint at the same time when you design an algorithm like a garbage collector. But some way, this principle doesn't take into account what happens to the actual end-to-end application performance. So if we consider the entire optimization space, we can actually find configuration that improve throughput, latency, and footprint at the same time. So I think it is an important concept to remember. So let's go to the third myth. I often hear this myth, actually. Should we still go and tune JVM in 2021? Why don't we simply use the newer JVMs, which offer constantly improved performance, newer low latency garbage collectors, and so on. Let's see what we learned here. So at Akamas, we do a lot of performance testing and benchmarking to understand how the JVM behave and how to better optimize it. So this time we did a simple experiment with Renaissance, which is a popular open source Java benchmark that is also used by the JVM developers. We ran the benchmark with a default configuration, again, G1 GC here, with increasing level of max heap from 2 gig to 5 gig. During the experiment, we measured some key metrics like the execution time, the garbage collection time or garbage collection overhead, and also the maximum heap that was used during the experiment. So let's see what happened. So first of all, the execution time decreases as the heap gets bigger. So this time is something that we expect, so no surprises here. But look at the GC overhead. It actually increases with bigger heap. So this is interesting. When we see high GC time, our first reaction that we all have is to add more memory. More memory means that the garbage collection has more room to allow for application allocation without needing to stop the threads. But again, this example shows that the JVM might behave in ways that are not necessarily what we might predict with our simple performance model that we have in mind. More importantly, it's interesting to observe the run with 5 gig. So in this case, G1 decided to use only 3.4 gigabytes out of the 5 available, as you can see. So this is very interesting because on one side, the garbage collection overhead was already pretty high. It was close to 20%. So the garbage collection was stopping the application thread for 20%. But at the same time, G1 decided not to fully inflate the heap, not to fully take advantage of all the memory that it had available in order to conserve, to be in a way memory efficient in this case. So as you can see, G1 used a significant amount of CPU also. As you can see from the seconds of CPU time, this translates to about 80% of one single CPU core being constantly used to do garbage collection work here. So what does that mean? So as you can see, G1 traded off basically CPU and garbage collection overhead, which means throughput, to be more memory efficient in this case. But what if we wanted to have lower CPU footprint, for example, or achieve higher throughput? So G1 decided to prioritize a different kind of goal here. So this example shows an important concept that we need to keep in mind. The JVM is actually a complex machine, and there are a lot of internal heuristics that are used to navigate the throughput, performance, and resource and footprint trade-off. But the JVM decision might not necessarily be aligned with our goals. But luckily, we have ways to actually tune it with the parameters. So I have another very interesting data point that I wanted to share with you. So what you can see here is a discussion among OpenJDK developers about a proposal to change the default value of a parameter. The parameter in question is called max inline level, and it's an important parameter that affects the just-in-time compiler of the JVM. The just-in-time compiler is a performance-critical part of the JVM, which is responsible for compiling Java code into machine code during the code execution. So I've always wondered how the JDK developers actually make such hard decision. How do they choose the default value of such a performance-critical parameter? So as you can see in the discussion thread, that you can also have more details going into the actual Bugs website, and you can see here the link. The developers of the Java, of the JDK, decided to go ahead and increase this performance-sensitive setting in the next JDK release, based mostly on internal benchmarks. What is striking to me is that they clearly state that there are risks that for some applications, this new default value might cause performance regression, and they say that real application data is needed for sure. But they decided, nevertheless, to go ahead and change this setting. Now, I don't want really to pick on the OpenJDK developers. In all fairness, it's very, very hard to improve the engine that powers millions of Java applications without causing any issue. But I think this is revealing to understand the process that is being used to identify the default settings of the JVM and why we can actually have the necessity to optimize the JVM parameters. So the default values might be designed to work well for benchmark or at least a subset of production application, but they may be well far from the optimal for our own specific application. So the JVM are constantly improved and evolved, trying to be highly performant in every possible scenario. This is true. However, the data that we have clearly shows that default parameter behavior might be pretty far from optimal for the specific application and requirements that we have. So it's important to recognize that we have this optimization space, and it's relevant. It's probably going to stay there also in the future. So let's now move to the fourth myth. This is the last myth that I will be talking about. So this time we will be talking about cargo culting JVM configurations. What does it mean? It basically simply means that we see a lot of developers that are actually copying and pasting good JVM settings that work well for a given application scenarios to other application scenarios, and those becomes the new default for their own organization. Java virtual machines. Here I want to mention actually two lessons that we learned by looking at some false myths that we really encountered in some of our customer engagements. One myth is that we have seen is that people is actually trying to tweaking the number of garbage collection threads, which we have seen is the first myth. Those are the number of threads that JVM is actually using to perform GC work, and they are tunable. They are an important JVM tunable. And one of the things that we have noticed with some customers is that they have this kind of rules about how many threads the GC should actually use. So in this case, the myth was, or at least the belief was, to let the JVM use half the amount of actual CPUs that machine has, in the hope of not impacting the application performance. Well, the confusion here is that we need to consider that we have different kind of GC threads, as we have seen in the first myth. We have the parallel and we have the concurrent ones. So if we reduce the run type, we might increase the garbage collection pause time, and we might actually wrongly, in a way, impact the application performance. This whole tuning may get a little bit more tricky in container environments where you don't have a clear definition of how many CPUs your container actually has. This is also for Kubernetes. We are talking about these weird performance issues that can happen on containers, like undesired CPU throttling last year at the PAC. So you can go and check it out if you are interested. So the other kind of cargo cult that we constantly see is setting the heap size, in particular the initial heap size of the JVM equal to the maximum heap size of the JVM. So basically, JVM lets you basically set the maximum amount of memory, the max heap, but it's also allows you to set the initial heap, which is the initial amount of memory that the JVM will use as soon as it starts up. So this kind of best practice is actually a high performance best practice that is very commonly used and found also in products. The problem is that if you do that, there's a pretty interesting downside that we learned. So if you apply this best practice, as a matter of fact, you are actually turning off a series of strategies that modern JVM actually use to actually be more memory efficient, which can be an important aspect for JVM when running in containers, for example. So the JVM has always been considered a kind of memory hog, and we see lots of complaints among developers about that. But the reality is that, again, it comes down to the trade-off and the default settings that today are very much geared toward max performance. But that is changing, as we have seen in the third myth, where we have seen Jvm, for example, was starting to prioritize memory efficiency at the expense of performance or CPU usage, for example. However, what is less known is that the JVM can actually be configured to be a memory efficient as well. So there are a couple of parameters at play here. So this could be a topic for another talk, but you can refer to the links. There's a great Red Hat blog post on the OpenShift blog that talks about those kind of parameters that you can actually play with to actually instruct the JVM that you are more likely to be interested in, for example, in memory efficiency instead of maximum throughput kind of settings. So again, this practice of cargo culting JVM options, I think it should really be avoided. as different applications may run on different environments and may have different performance goals. So we see lots of developers doing copying and pasting configuration actually today, probably due to the complexity that is involved with the JVM tuning, as we are talking about. But actually, these kind of bad effects can really multiply. For example, if you have lots of services or microservices, this can really have a bad impact on the overall application performance or infrastructure cost. So that is about it, about the talk. So let's wrap up. So what did we learn actually in this talk? So I guess we can summarize it as follows. So JVM tuning is actually a hot topic today, and rightly so. I guess we have seen that with lots of real-life example and benchmarks data that we have pretty significant benefits by tuning the JVM on application performance, infrastructure costs, infrastructure utilization, enhanced infrastructure costs, but also on reliability. And all of that can be reached without touching application code. So today, we as performance engineers, we need to, in a way, to tame the complexity of the JVM. So how do we do that today? We all use best practices and our basically intuition, the lesson that we learned in our experience. But as we have seen in this talk, these very same best practices actually are not universal laws, and they can be wrong in practice. So they can lead us in the opposite direction. So we can lead us leaving significant performance optimization potential on the table. So as performance engineers, this is kind of bad news, because we use performance models to reason about performance of our system. But I think we need to recognize that IT systems are becoming more and more complex, and to base simple performance models might no longer work. But in the end, I think there is actually hope. I think that in the future of performance engineering is bright, as we have new tools on the horizon like AI that can really help us in changing the level of the game here to tame this complexity and also automate more activities that simply are too complex for our human brain, but still being able to deliver more and more value, as it will allow, for example, us to exploit the optimization potential that is kind of somewhat hidden in our system. And the kind of best practices that we use today are not really effective in unlocking this kind of big potential. So that is it. That is the end of my talk. I hope you enjoyed it, and I'm now open for questions.
Thanks, Stefano, for your presentation. It was an awesome presentation. We have 2 other PAC members connected, so I'm going to enable their webcam and mic. So we have Taras Biri, who will be the next speaker, the next performance rockstar. So, Taras, do you have any questions for Stefano?
Yeah, actually, I do. By the way, basically the idea is that the only thing that is always true for performance advices is that they always become invalid at some point of time. Like, they change. It's not something that we can just state and expect to be the same without any changes in the future. So I wonder if you have some, I don't know, kind of like a continuous testing service or whatnot, similar to, for example, what Google has with fuzzing, which automatically fuzzes the applications on a continuous basis to make sure that new regressions are identified. So I wonder if you have something like that as well as a service to make sure that whatever advice you give remains correct as time changes.
So are you meaning Taras, about auto-tuning, continuous tune optimization?
Right.
So that's part of the pipeline where you make a check that see if the settings were correct on the previous release.
Yeah, that's a great question, actually. So tuning, of course, is not a one-off exercise. So you need to constantly being able to maintain the level of performance and ensure that the software that gets shipped to production is actually always efficient and as performance as it could be, because actually most of the time developers in the DevOps, in a way, movement actually focus on, of course, on automating functional test, then it comes a performance test. But at the end of the day, they just check that some kind of performance is actually SLA or SLO is matched. But we may risk of shipping actually the new artifacts which have code that is changed, so maybe very different with respect to the previous release, without actually changing the configurations. But as we have seen, they play a pretty significant role. So we need to ensure that they are always in a way matched with respect to the application code and the workload that we expect, so that we are not actually, do not risk also to lose performance and cost efficiency on one side, but also reliability is also affected, because actually if configuration are wrong, and maybe, for example, the result of a manual tuning did last year, now the code is completely changed. So chances are that you are also running the risk of having service disruptions by keeping the old and state configuration. So of course, this needs to be in a way integrated into the pipeline, and this is something that we do it with Akamas actually. Yes.
But the questions from my end, because I'm thinking if you do auto optimization on every single releases, it could take quite a significant time. Maybe not with Akamas, it may be 10 hours, but still, I mean, if you have a pipeline, that could be a very blocking task. Do you think that we could come up? I mean, I don't think we have an answer, but if we can come up with rules that will check on the code review, for example, or a couple of coding concepts that have changed, and then that will make a flag saying, okay, this one, obviously those concepts has been introduced, so we know that the previous settings that we had won't be meaningful, so we have to maybe redo the tuning. I don't know. I mean, do you think that we could come up with something that could be worse for our other projects? Because I think if we do every single release auto tunings, that could be, I can see that some of the companies will say, yeah, I'm not ever going to take 10 hours of every build. That will be very expensive.
Yeah, that's a great question. So actually, the way that we see it is that, of course, we by integrating in the pipe, we don't mean actually starting a kind of tuning process for every single commit. So it doesn't actually make sense. So one of the way that we see it, for example, being able to optimize the release before at the end of a sprint. So for example, depending of course on the kind of delivery models that people have in place, but for example, at the end of a 2-week sprint before releasing to production, it might be worthwhile to spend some hours to actually optimize and make sure that all the settings are in place. By the way, we also have capabilities into the within our AI to being able to learn from past experience. So this is a kind of continuous tuning, but it can leverage the knowledge that we acquired in previous optimization exercise. So it's not that we start from scratch for every single time. So this is something that we can do. Then, of course, really the ultimate way would be more along the line of what you were suggesting. So also being able to understand more at the commit level where we need to trigger an optimization like this one, because perhaps there may be the need to for specific in a way commits and smaller amount of code that gets checked in, we might need to trigger some optimization. So I see an evolution of being able to more automatically also invoke the optimization. So an automation of the automation of the optimization.
And so you something that brings my interest. So you're saying that if you tune one version with Akamas, so you mean that if I relaunch it on the next release, Akamas won't start with from scratch. He will start with the previous results and configuration settings. So basically, instead of 10 hours, maybe in 1 hour or 2, you can have already everything tuned up?
Yeah, it's something that we already have capabilities to do that, to learn from the past. So in a kind of pipeline context, it's something also that we are improving. So it depends, of course, on how many changes, how the entity of the changes of the application. We are also working on extending our algorithms to being able to detect these kind of events and being able to identify that the fact that the application has changed or the workload is changing, and keeping those information also or feeding those information also to improve the outcomes, the time to converge or the best value that we find, etc. Yes.
So Taras, maybe from with your experience and the work that you're doing at Facebook, how are you doing this? Do you also have an automatic process, or is it based on the release? You say okay, now we have to optimize everything.
So we do have multiple layers of testing for when it comes to performance. We do have things like, obviously we try to move as many things to the left as possible, so that ideally you wouldn't even be able to land the changes that are causing some performance regression. So we do have some battery of tests, performance tests, that are pretty fast so that they do not delay the integration experience. But then we also have multiple layers of analysis tools. One is running on a continuous basis on our test environments, which is trying to identify some performance regressions for other more involved tests that take more time. And we also have production data. We try to, basically the biggest challenge with synthetic testing is the fact that they may not always be representative of the real world use cases that we care the most about, because ultimately our goal is to make sure that the customer experience is great and not our metrics are great, because who cares about our metrics if our customers are not happy? So we do have profiling enabled for all of our applications, obviously, and we do have machine learning pipelines that go through all the traces that we have, trying to identify any regressions that we may have. And we have separate pipelines that are specifically targeted at certain permutation level optimizations. Like, for example, one of the most meaningful one is probably the application layout, because depending on how you load classes, for example, in Java, you can have a significantly different cold start experience, because obviously things are loaded in pages. If you can batch the classes that you have to load at the very first seconds of your bootstrapping in as few pages as possible, you get the cold start wins. So we have fairly advanced machine learning in that stuff. And we also have runtime optimizations where we do look at things dynamically, like, for example, even the temperature of the CPU or whatnot. And depending on that, we can decide whether we want to maybe force turbo boost mode on the CPU or throttle it to avoid overheating or whatnot. So there are many layers at which we're trying to optimize things, and they are extremely valuable for our performance work for sure.
So you're trying to mix performance and green IT in the same time.
Yeah. I mean, usually there is a strong correlation because obviously, you usually improve performance by doing less work or doing it more quickly. And when you do that, you usually also conserve resources, which means like you either reduce the energy consumption or memory consumption, because memory is actually a pretty big deal. Like the less memory you use, usually the faster you run, just because like more things fit into the caches and fewer things you have to load into the memory. And in general, there is this perception that our CPUs are slow. Our CPUs are amazingly fast. It's usually the memory and other crap that they have to wait for that is slowing down the CPUs.
Yeah. In fact, there's no real CPU. It's more you're waiting for something in a network or you're waiting something elsewhere. Yeah, that's true. And but by the way, we because we talked about this concept of green IT, I think it was last year. Do you have sort of in performance, people are using AppDex to see how fast is the rendering, the performance? Do you have like a similar index to sort of score how green your release is, or is it something that you just extrapolate with the performance level?
Who is this? Like, is this question for me?
Yeah,
or
you, because it was related to the green IT, in fact.
Oh, well, unfortunately, it's tricky, I guess, just because I don't think we have such a concept, at least well defined. So for the most part, we do have a bunch of consumption metrics, as we call them, that we care about, which also include energy efficiency. But we do not have like a benchmark that we are striving for. We just try to, reduce the energy usage as much as possible, and that's like the goal. But obviously, there are lots of trade-offs, especially when you deal with performance. You can sacrifice, oftentimes there is a balance between how much you can get speed up during cold start versus when app actually starts. So you can trade things by, for example, delaying them to a later stage. So you're gonna win at cold start, but then your first interaction experience may potentially suffer just because now you have to actually do that work. So it's tricky to set these metrics just because you usually incentivize people to game them. And that's actually the biggest, I guess, challenge with benchmarks in general. I think it's actually very common in our industry to see how many companies are trying to game the benchmarks, even though they actually kind of suck for end users. But obviously, if your buying decision is based on the benchmark, then it creates this economical motivation for gaming the system, which is super unfortunate, I think. That's why we try to, I guess, move away as much as possible from the synthetic metrics towards the production profiling and sentiment measurement. Like basically whether our users are sad or happy. That's what matters in the end of the end. So we try to measure our performance based on those metrics.
All right. So we have 8 minutes left before your Tara's presentation. So I would like, first of all, to thank Stefano for your presentation. It was very instructive, a lot of content, and I think there will be a great blog, to be honest, so people can utilize and take advantage of that. So thank you so much for your time, for building that content, and again being part of the pack again. Thanks, Stefano.
Okay, thanks to you, and thanks for the nice words.
Yeah, thank you so much. And by the way, can I ask one more quick question?
Sure.
So basically, so first of all, like this is amazing service. I absolutely love, the promise of free wins on a continuous basis. I think that's one of the reasons why I was at some point extremely excited about Java in general, just because you get all these wins all the time from the improvements of the JVM. But this is way better because JVM is not able to improve things as quickly. But I remember in JavaScript, there were a lot of interesting websites where you could just paste your code, and then it's going to benchmark it and you can have some sort of like portfolio of things that implement the same idea, and you can have ranking based on their performance. So I wonder if you considered using Akamas for something like that as well, where you are able to maybe just showcase the automatic tuning features on a free website where people can just maybe paste, like, there is a Debian, I think, benchmark, language benchmark or something like that.
Okay.
Yeah, so have you considered maybe doing something like that as well? Just to showcase.
It might be an interesting, it might be an interesting idea. So I know the language benchmark that you were referring to. It's actually being used also. I've seen benchmark for the Go runtime also, Go versus Java, etc. They are all using this suite of programs because it's the only standard way to compare different languages, etc. That might be an interesting idea actually, to see what will happen. So for what I've seen, those are typically very, very simple algorithms. So it has to be seen if they are still realistic to see if we can match in what we are seeing in more real life productions. But it could be a nice extension. Yes.
And maybe also having some sort of portfolio where you can have maybe even the exact same program that you can even write yourself, but then you continuously run Agamas on it and provide some sort of like, here is the best advice for this code at the moment. And then you can also see in the history how the platform changes, like, for example, how the JVM changes affect your decisions. And so everyone can see like, oh yeah, looks like this is really cool. Like, it automatically found the best GC or automatically found the best Eden size or survivor size, like all these things. That would be really, I think, cool for geeks like me. I would really love it.
So that's great. Thanks for the suggestion. We actually have this kind of capability is more in line to what we provide in the platform. So you can actually see over time how the different best settings evolve and how the performance level actually goes up as the AI actually is able to explore more of this huge space and find the global, all the local optimums up to the global one. So it's something that we have, and yes, that's so. I guess it's so fascinating because actually we have this. The nice thing about the JVM is that it's so configurable. So you have this very big configuration space that it's really showing this whole variety of goals that you can explore. So sometimes you want to save on infrastructure costs, or at some other time you want to minimize the latency. So you have these very powerful ways of extracting more performance. But by the way, it's not just on JVM. Of course, we did actually last year or 2 years ago similar kind of talk about the cloud. For example, being able to select the best cloud instances. Again, pretty much same, not the same complexity, but today, for example, on AWS, they are still adding the new kind of instances that you can spin up. And I guess today's they are about 200s and kind of thing with all the different kind of CPU, all the different kind of memory and network and storage. So again, it's becoming also there a puzzle to understand how to optimize that. So it's becoming more and more complex actually, like pretty much across the board.
Don't forget about the presentation that Luca did last year on Apache Spark. I mean,
on Spark, yes.
Yeah, it was also great topic as well.
Yeah, Netflix actually wrote about how they find the best instances for their workloads. Just because, like with cloud, it's extremely important to find the best resource that fits your needs. Sometimes you need more memory, but maybe CPU doesn't matter. But sometimes it's the other way around, and you can overpay and get a worse service potentially. if you don't pick your instance correct way. So I think, yeah, that's definitely an awesome use case for these automatic tuning. So I'm looking forward to seeing more features added to the command platform.
Okay, thanks a lot, Taras, for the suggestion. Okay, that's great. Thanks a lot, and thanks again for having me, for having organized such an awesome event.
Thanks.